Welcome. Continuing our problem solving sessions. I have here two reactions which have products that are looks like a substitution in the top one of by bromine, and here also it's a substitution by bromine. What happened in a chemical reaction is bonds would be broken and bonds would be made in the product. So in calculating delta H, or the bond dissociation energy, we have to clearly know what bonds are made and what bonds are broken. Before I solve the problem mathematically, I'll just show you what bonds and how they might have been formed in these reactions. So this substitution, this is an alkane, and you have a bromine molecule. So in this reaction, in most cases, I will discuss it in the future, this is an alkane. And there is no any heteroatom on it. They are usually unreactive. So usually the only kind of reaction they are prone to do is a free radical reaction. That means there is a bond that will be broken homolytically. So I will just show you CH3, H, and this H. So this bond would be broken. So that is a bond we are talking of. So I will say here, bond broken in the top reaction, CH, that's what is being broken. And another bond that's being broken, this is, I told you, you don't have to know exactly now, but this is broken homolytically. That means it is converted into F2 radicals. So that is a bond that's broken. Here also, for the reaction to happen, the Br-Br bond have to be homolytically broken. So bond broken, bromine, bromine. In the product side, if you just look at here, what is being made is the carbon-bromine bond. I'll just leave this, but the one which is made is this carbon-bromine. So bond made is carbon-bromine bond is made, and also a hydrogen-bromine bond is also made. So HBr is made. So in this case, now in the equation, delta H equals adding all of the delta H that are broken and adding up all the delta H that are made. So usually these are given in a tabular form in reference materials. So I will just look at here the reference. For carbon-hydrogen bond, we need 410 kilojoules per mole to break. And the Br-Br bond is 192 kilojoules per mole. You can find this in a reference book or at the appendix of your textbook at the end of the pages. And the CBr bond, when it's made, it is minus 285 kilojoules per mole. It tells us that bond making is an exothermic process because you are generating a more stable situation. and the HBr is minus 368 kilojoules per mole. What it tells us is all of the bond making are negative, that means exothermic, and the dissociation energies or the bond breaking energies are all endothermic, meaning that you need to put more energy into the system. So in adding all of them, the 410 plus 192 plus minus 28 to 185 plus minus 368, all of this, when you add up at the end of the day, you'll get a minus 51 kilojoules per mole. So minus 51 kilojoules per mole. That means the forward direction, the delta H for this reaction is minus 51 kilojoules per mole. That means it's exothermic. It can go spontaneously during the reaction. So it shows you that is heat releasing. This reaction releases that much heat. At the end of the day, after bonds are broken and made, you'd get a net energy of release of minus 51 kilojoules per mole. Therefore, that reaction I would term it as exergenic or exothermic reaction. So similarly, I'll be solving the same for the methanol reacting with HBr, hydrobromic acid, hydrogen bromide acid, to form methyl bromide and water. So here, the bond that's being broken, obviously CH3 is still there, a carbon-oxygen bond is broken. So for bond broken, in the next question, carbon-oxygen is broken. And HBr, in HBr here, CH3OH. So this is the bond that's actually being broken, carbon-oxygen bond. And here, HBr is being broken as we just look at it. And here in CH3Br, carbon-bromine bond is formed. Here HOH is being made. So this is a carbon-oxygen that's being broken. So in HBr, that's the bond that's broken. And for bonds made, CBr, carbon-bromine, and for water, this is what's being made. So now we would be just calculating for each one of them. I just have to look some numbers here, and CBr is minus 285. It's the same thing like above, kilojoules per mole. You can check this if I made a mistake. And this is minus 498, very exothermic, making water molecule. And for carbon-oxygen bond, the breakage of carbon-oxygen bond is 389, I believe, 389 kilojoules per mole. And for HBr, 368 kilojoules per mole. So delta H equals bond breakage is the same sum, 389 plus 368 parenthesis plus minus 285 plus minus 498. So the net is, from what I calculated, is minus 26 kilojoules per mole. Kilojoules per mole. So still, this reaction is also exothermic. So the product formation is favorable to make that reaction. So this is how you would be using bond dissociation energy to calculate enthalpy of a reaction. So with this, I'll continue to the next. I have another important question, and it is asking us, explain why the bond dissociation energy between this carbon and that carbon is 356 kilojoules per mole in propane, while in this carbon-carbon bond dissociation, it is 385 kilojoules per mole. So clearly, as you see, the bond dissociation energy required to break this bond is higher than this by close to 20 or maybe 20 something kilojoules. So what is the explanation for the difference in the bond dissociation energy in these two compounds? One is propene. This is one propene, an alkene, ENE, remember this, ENE, propene, but this one is propane. Okay. In propane, the bond dissociation energy is less than the bond dissociation energy for this carbon. So the indicated carbon is what we are looking at. So here the explanation is very important in terms of concept for the future. So if you just look at the hybridization of each carbon, I'll just say hybridization of this carbon is sp3, this carbon is sp3, this carbon is sp3. And in this carbon, this is sp3. However, the middle one is sp2, sp2 hybridization. So the bond strength depends also on bond length. So the bond length between sp2, sp2 hybridized carbons is not the same as between sp3 and sp3. One important concept you should remember. Bond lengths between two carbons that are sp2, sp2, carbon-carbon double bond length, and carbon-carbon single bond is not the same. This is much longer than this one. This is shorter. In addition to that, the strength between sp3, sp2 carbon, or still also the length is not the same between sp3 and sp3, between sp3 and sp2. So bond length sp3 is longer than sp2 bond. Strength wise, bond strength is similar. sp3 is weaker than sp2 hybridized carbon. This is important. So no matter what kind of organic structure you see, you can easily predict if you know only these facts. This is a fact. So also now what we are asking is the bond strength between sp3 in question 1, sp3 strength-wise is not the same as sp3, sp2. They are not equal between sp3 and sp2. So definitely that is where the difference in bond dissociation energy comes from. So this bond is a stronger bond than this one, and shorter also, shorter lengthwise. So that can explain this. We have a rationale why that bond dissociation energy would be higher for propene than for propane. This is a very scientific explanation of the bond dissociation energy difference between the two based on the hybridization of the carbons that are involved in those molecules. So we'll continue with another problem. I have another question which says draw a resonance structure for homolytic cleavage of these compounds. The indicated bond that would be broken is the carbon-hydrogen bond. So when it says a homolytic cleavage, this is what happens. Homolytic cleavage of this for the indicated bond. It could be anyone, the carbon-hydrogen bond. It means that you are doing this, doing this. What you would be forming would be CH2 radical CH2. So if you just write it in a very common way of drawing, you have this. Two hydrogens right here and a radical. Obviously there are two hydrogens here. This carbon is right here with H. So that's equivalent, they are the same thing. But the question is, for this product, you would have a resonance structure. Resonance structure, we should be reviewing that again. I will have a supplementary note about resonance. It's also a very important concept in organic chemistry. So this is participating of the free radical over all the compound. So this is a characteristics of an sp2 hybridized carbon. sp3 hybrid carbon doesn't do it. So sp2 carbons, they do it. So let me see by moving the electrons. So now this single radical would come in here, and one of the electron would also participate in coming here. It leaves the radical here. So the resonance, it's a double arrow. What we have formed is we made a bond, a double bond, and the free radical came here. So there are two hydrogens here still. CH is still here. But what happened is a new bond was formed here. So what I have done is just push the electron to participate in bonding that free radical after cleavage. That's what it says. And then one of the bonding electrons also participate in bond forming. So these are equivalent structures. There is no distinction between these two. They are resonance structures. This is not a reaction. What happened is this structure lives or exists as a hybrid of all of these resonance structures. So when we say a resonance structure, we meant that a innate structure, what we see on a board or anywhere, is a net sum of all the combination, the hybrid structures, all are incorporated in that structure. So there is a way where this electron is residing between all this carbon. So it is going back and forth in the resonance. If you just look at it, this is a characteristics of only sp2 or sp hybrid carbons are the ones they can do this. sp3 cannot do resonance. sp3 hybridized carbon saturated, that is a saturated bond, cannot do resonance structure. So there is a way, since this radical is moving here and there, it's being delocalized. Resonance structure stabilizes the structure by electron delocalized. So the electron is not localized on one carbon, it is delocalized. So the delocalization is seen by this kind of symbol. So what we do in organic chemistry is that we do it, this is a flow of electron, it shows that, and what is moving back and forth is this. So this is another representation of the delocalization. So delocalized electron. That's what actually resonance does. It delocalizes the free radical or the charge or the pair of electrons. So we'll do more examples as we clearly see how we apply resonance. So this radical is resonance stabilized, meaning that it can go in any direction and stays in one without any distinction. So this is a delocalized electron picture. So this picture is a delocalized electron flow. That's what you see. So resonance, when a certain species has more than one resonance stabilized structure that we can draw, that is a stabilizing effect. It stabilizes that radical, that charge, or that negative charge. So this free radical is now being delocalized across the three carbons without any problem. So rather than being, for example, if you have a sp3 hybridized carbon, so out, saturated, and you have a radical formed here, you cannot push this electron to this. There should be a pi system that also interacts with that. So no resonance for this, no resonance with sp3 system. You need a pi system, sp2 system to make. So because if you just push that electron to this, you don't have any other one pi system to push electron. The sigma, if you want to push this, you are breaking the bond. So it doesn't participate. A sigma bond doesn't participate in a resonance. Sigma bond cannot participate in resonance. Very important concept. You cannot make that electron to be delocalized over the pi system. You don't have that. So sigma bond cannot. This is very important concept. So that's the delocalized picture, the same equivalent. It means that the structure of this propene radical, one propene radical, this is a propene radical. This is a propane radical. Propane radical. This propane radical is very, very unstable than the propene radical, because the propene radical can be resonance stabilized. It can go back and forth over the three carbons easily. So if I ask you a question, which radical is more stable? The one which you can draw a resonance for is more stable. So propene radical is more stable than a propane radical. So we'll continue with another. Welcome back. We start also now by showing all possible radicals for this compound, which is propane. So a free radical is formed when a carbon-hydrogen bond is hemolyzed. Homolytic cleavage of, for example, one of these hydrogen would result in the formation of a radical. The other possibility is if the free radical is generated from the second carbon. CH3. Taking a radical from here is the same as taking what we have done. So the only possible free radicals in propane are on these two carbons. So this is removal of one of the hydrogen radical, removal of hydrogen radical. So basically the bond dissociation energy for these two carbon-hydrogen bonds looks like it's different, because if you just look your table, the 410 kilojoules per mole is for this one, and for the middle one it's 397 kilojoules per mole. So they are quite different. Still, this is carbon-hydrogen bond, but they are different. This tells you that this carbon is a secondary carbon. This carbon is a primary carbon. So the amount of energy that's required to remove or to break a primary is much higher than a secondary. This is what we see. So primary needs 410 kilojoules per mole, but the secondary one needs 397 kilojoules per mole. And these are the type of free radicals that are formed. So I remind you again, this is primary because this carbon where the radical is connected only to one carbon, such carbon is called a primary. Therefore, the radical is also called a primary radical. Here, the carbon is attached to two carbons and one hydrogen. This is secondary. So, in a sense, the conclusion is secondary radicals are stable than primary. We even can conclude that even if we have an example of a tertiary carbon example, this tertiary butyl radical is unusually stable. So the formation of this is a tertiary one. I just included this as an example. So a tertiary butyl radical, this is tert butyl radical, is most stable. If you just compare this primary radical, secondary radical, tertiary radical, this is easy to form. So the bond dissociation energy for this would be much, much less than what we have for the primary and secondary. So from now on, remember, forming a radical, which is a bond dissociation of carbon hydrogen, is much easier for a tertiary than a secondary than a primary. So bond dissociation energy is much less for a tertiary carbon, such as this one. So this is a tertiary radical. So I want you to remember the nomenclature. Now we have introduced this question, a primary, secondary, tertiary radical. And the bond dissociation energy is much low that's required to break a carbon-hydrogen bond on this, for example. What I mean is, if you have this H, to break this and generate a free radical is much easier than a primary, which is not stable. Next, this is a little more stable than that, and this is the most stable. So when you generate a free radical, you have to have a reason why a certain radical is formed, while the other cannot be formed because it requires a lot of energy. So we'll continue. Let's continue solving some problems still. So here are some thermodynamic values for a reaction of A going to B. This is just a model reaction where starting material A is going to B. So the question is, there are conditions A to G, and the question to you is, just by looking at the equilibrium or the thermodynamic constants that are given here, you want to predict which way is the reaction going. So if this was an equilibrium reaction, A go to B, the double arrow shows that equilibrium. So we want to predict the direction, which side is favored. Is the B formation of B is favored, or going back to the formation of A or starting material is favored? So I just want to put one equation here, which is delta G equals delta H minus T delta S, one of the equilibrium equations we know. And the other one is delta G, which relates to equilibrium and temperature. These are the two important thermodynamic equations that you can apply also in any other calculations. But for this reason now, it shows K equilibrium of 0.5. So let's see, K equilibrium means it is the ratio of products B over ratio of A. So the product side is favored if the upper numerator is greater than the lower one. So K equilibrium 0.5 means that it is 1 over 2 ratio, meaning that for each one is formed, still there is 2 of A. K equilibrium should be always greater than 1 for reaction to proceed to the product side. But what you have is 0.5. So the reaction favors, in this case, it favors starting material because it's less than 1. Starting material, I would say A, favors formation of A. It's going backward because the ratio should always be greater than 1, at least in the forward direction. And delta G in the next condition of minus 100 kilojoules per mole, obviously delta G less than 0, which is negative, exothermic, it should favor the product formation. It's an exothermic reaction, delta G overall it is less than 0. So delta G is less than 0 favors product, favors B. product formation. So the reaction is favored in the forward direction. Next, C, it says delta H naught, one of the factors, enthalpy of a reaction, is 8 kilojoules per mole. As far as enthalpy of reaction, this reaction looks like it is endothermic. So it's not, this is positive. It's not exothermic. So it favors, at least considering only enthalpy of a reaction, it is positive. So delta H greater than 0, meaning it favors backward. It's not exothermic in the forward direction. It favors A, considering just that. D, K equilibrium is equal to 16, which is very large. K equilibrium is greater than 1, hence it should favor product formation. So it favors formation of B, or the product. The product is favored to be formed. Delta G equals 2 kilojoules per mole. That is very low positive number. So it's delta G greater than 0. Delta G is greater than 0. It's not favoring product. It favors the backward reaction. It favors A. So it's endothermic. Hence, it should favor backward. Delta H naught, 200 kilojoules per mole. It really is very endothermic reaction with that much positive enthalpy. Delta H still greater, much greater than 0. It favors A, meaning the starting material is favored. And in the last one, G, entropy is 8 joules per K per mole. Joules per Kelvin per mole. For the first one, since entropy is positive, remember, if entropy is positive, temperature is positive always. So this is a large negative number. That means delta G tends to be less than 0, or it's a favor. So entropy increasing is favorable to form the product B. So entropy is delta S is greater than 0, hence it favors formation of B. In this case, delta S is negative, so delta S less than 0 should favor backward. So these are some of the qualitative. It's not very mathematical, but it just gives you the overall qualitative assessment of a reaction going from A to B based on these quantities. What do you predict? You predict the formation of a product or the going back to starting material. So we'll continue with another question. Let's begin with the problem you see on the board. This is a question on energy diagram and understanding mechanism of a reaction and understanding the enthalpy of a reaction and the rate determining step and all of that. So this reaction or the model question here would give you a very broader understanding of reaction mechanisms. So that's why I'm always repeating that students try to memorize a lot of reactions rather than understanding the mechanism so that you would apply to any kind of reaction. That's the best practice in studying organic chemistry. So here we have the energy diagram for a reaction, and I have summarized the reaction. The reaction is this tertiary butanol is converted to tertiary butyl iodide compound. So that's just a summary of reacting it with hydroiodic acid. But here is a breakdown of what happens at each step. So this reaction is not a single step reaction, it's a multi-step reaction. So that's why first we have to answer how many steps are involved in the reaction mechanism. So there are 3 steps. So I want to show you in these steps. Step 1 is the protonation. We call it activation of an alcohol. The first thing, the alcohol should be converted into a good leaving group. OH minus is not a good leaving group. So what we do in the synthesis or in the reaction, we activate the OH and convert it into a good leaving group. Conversion into a good leaving group involves reacting it with a strong acid. The strong acid would protonate that OH, converted it into OH2 plus, which is immediately leaves as water molecule. So the first step, step one of this reaction is activation of the OH group, that's the alcohol group, to convert to a good leaving group. Good leaving group. What happens is, in step 1, you are activating it using hydroiodic acid, so the OH would abstract one H plus from strong acid and becomes OH2 plus. So this is a product. The first step of that product is this product, that's the activation. So the transition state going from the OH to OH2 plus looks like you have tertiary alcohol, which is about to break, and 1H, which is already there, 1H, which came from the acid, HI, creates a sigma plus in the transition state that's about to leave as a full charge to be converted into a full charge. So this is the first transition state. That's converting it or activating it into this highly unstable species. So once you have that, it goes to the dissociation of I happens. I would leave, so the I is still around, stabilizing this. So I sigma negative. So it is this transition state. Now we have this intermediate, which also needed to be activated. So this involves its own activation energy. It has EA1, I would say. So this gets also activated. It takes this much activation energy, EA2. So the transition state at this point is the dissociation of this positively charged species. So what I will have is CH3, C, leaving OH2 plus, and this is a sigma plus, and that's what happens. And you have this starting to build up a positive charge. So that's the intermediate, which is forming a carbocation. So the second step is formation of a carbocation transition state, a carbocation, meaning C plus, very reactive by losing a neutral molecule, which is H2O. That's the second step. So carbocations are very unstable. That is the first, is a very reactive intermediate we have in the activation energy 2. So once we have the activation energy 2, the carbocation is ready now to get a nucleophile. It's very ready to get a nucleophile. So the nucleophile would attack this carbocation. So what happens in the transition state is CH3, 3C, and the iodine is about to form a new bond to be formed. So that would go through activation energy, A3, E3. Now, once you have all that nucleophilic attack, immediately the enthalpy of the reaction would be low and it form a stable product. That's what we have here. This is a stable product at the end. So there are 3 steps. So step 3 is nucleophilic attack of the carbocation by iodine minus. That's the new bond formed. Carbon iodine bond is formed. So there are 3 distinct steps to form or to go from the tertiary butanol to tertiary butyl iodide. These are 3 important reactions, steps that happens. So if you are asked the mechanism of the reaction, it means that identify each reaction mechanism, what happens, and show the energy associated with it. So it says label activation energy, delta H for each step, and the overall. So we have already, in the meantime, we have done this. This is the first activation energy where protonation happens. This is a protonation of OH in step 1. That is activation energy 1. So the associated delta H for this is a very, very small delta H here. So delta H1 is less than 0, but not by a very big amount. So starting material is here, the products are here, the product which is this. So the delta H difference is a little bit exothermic, not significantly different. But the next step, the dissociation of OH2 plus to form this carbocation, this is starting material, and the product is here. So the delta H is starting material is here, but product is right here. So product is here. So delta H2 is greater than 0. This is a very energy demanding step because delta H2 is greater than 0. It means endothermic. So this step is endothermic because the product energy is much higher than the starting material. The starting material is right here, but the product is highly positive. So the difference with positive energy minus that energy would give you delta H greater than 0. Now, how about the last step? The last step is the starting material is right here, but your starting material is right here, and product is down here for the last step. So this is the last step, but overall, the net delta H, this is delta H3, which is also less than 0, but the net one is the one you have your reaction started here, and your product happens here. So the net overall delta H is this. So delta H, not of the reaction, net or total is this, that much. It is exothermic, obviously it's less than 0. That's why the reaction proceeds. So starting material was here, product is down here. So delta H for overall the reaction is exothermic. Now the next one, it says draw transition state. We have already drawn each one of the transition states at each step, which is the rate determining step. Now, from our discussion before, what I have already told you is the rate determining step is the one with the highest activation energy. The step that demands you to put more or demands or requires high reaction energy, activation energy, is the rate determining step. So that is EA2, that is the water molecule leaves and form a carbocation. Carbocation formation, step 2 is the rate determining step. We call this rate determining step. That is the slowest step. High EA2 activation energy, high EA2. So the rate of this overall reaction going from tert-butanol to tert-butyl iodide is rate limited by the formation of a carbocation. So in any substitution reaction of this type, you don't have to know for every organic alcohol. Now the mechanism is the same. If you have an alcohol of any kind with OH functional group, the reaction that it can undergo is a substitution reaction of that sort, for example, is the same for any kind of tertiary alcohol, where the second step, which is the carbocation formation, is the rate determining step. So that rate determining step is the one which needs high activation energy, and that is the intermediate that forms the carbocation is the rate determining step. So you need to review, this is a three-step reaction. Initial activation of OH as a leaving group, second formation of carbocation, third nucleophilic attack of the nucleophile I- that to form the carbon iodide new bond. No matter how complex it is, if you see any tertiary alcohol and you are given any strong acid, you should propose this. It cannot do any other reaction than in these three steps. So the only thing you have to memorize or remember and understand is just the mechanism. You don't have to remember all the organic alcohols and what they do. So from now on, what you should establish or need to establish is any organic alcohol, especially of tertiary alcohols, if they are treated with any acid and a nucleophile is around, they're going to substitute with that nucleophile through this kind of mechanism. So it shouldn't be very complicated or overwhelming to understand a substitution reaction on alcohols. This is a mechanism and the associated energy diagram. So these are the only facts you need to remember when you see such a reaction. So we'll continue more with solving some more problems.